All right. Well, we have some important things to do today. Let's see. Hold on one second. If I recall correctly, we didn't quite finish the chapter 12 problem set. We'll do that right now. And then we are going to do the sample final. All right. So let me get those open. So this, here's the chapter 12 problem set. And we did not quite get to the second problem. And then, of course, the sample final, we haven't done it yet. So we'll do that right now. So now when we're done with the sample final and this problem set, then we're really and truly completely done. There's only one last hurdle, and that's the final exam. Now, of course, if this was a normal semester, we would come back sometime next week and actually take an exam in the classroom. But of course, this is not normal times. So instead, as soon as we're done today, I'll post the final on Moodle. And then I would say that you'll have a minimum of a week to get it done. Now, I think I might be able to stretch that out a little longer, but let's just assume that a week will be plenty for you to finish it up. It's not that long. It's only the last two chapters. So let's just say that tentatively we'll assign the due date as next Thursday, which is the 13th. All right, well, first let's go look at Moodle for a second. So let's see, what are we looking for here? I just want to make sure everything's where it belongs. For example, as far as the exam goes, you did two parts of the chapter 11 problems. Okay, so their solutions are right here. And then we're finishing up right now the chapter 12 problem set. Okay, those answers will be here. In fact, they're already here. And then the only thing that's missing, it will be that I will have to post the solutions to the sample final when we're done here. And then I will also post the actual final exam. And so let's say that it'll be due next Thursday. I think that's plenty of time. In fact, why don't I do this? Just to make sure there's no doubt in anyone's minds. So the final exam will be due at midnight on Thursday, 5/13. Now that should do it. All right, so if you forget, just come here and look at this. I don't know if these announcements automatically generate emails to you or not. But if not, it's okay, because you'll have that right here. There's a permanent record of it. If you say to yourself, oh, I don't remember, you can just come here and take a look. And there you are. All right. So now, that being the case, originally we were scheduled to have one last class next Monday. But now, since we finished a little early, there's really no need for that. So you can just sleep late next Monday if you want to. But having said that, if you're stuck on something and you need more information, you can send me an email and I'll take care of it. All right. So today then is the last time we're going to meet. Okay. So I was just announcing that today we're going to wrap up the final exam, or the sample final rather, and the chapter 12 problem set. And so I will, when we're done, I will post the solutions along with the final exam, which will then be due a week from today. In other words, it'll be due on midnight, May the 13th. And because we're finishing it up today, we don't need to meet again next Monday. Okay, so officially Monday would have been our last day. No, it's just this usual format. Just take it home and do it, and send it back when it's done. And also don't forget, it's only chapters 11 and 12. That's all. We're definitely not having a comprehensive final for this class, that's for sure. And so it'll be the usual format. You know how it is. You download it, you work on it, you take pictures, send them back, and that's how it works. All right, so let's get to it. So chapter 12, number 2, this is the one we didn't quite have time for. We have a population with the following elements. You can see I've already started to write in the solutions here. So for example, for the population mean, we use the formula that we've been using all along. This is the population mean. You can tell it's the population mean formula because it has Greek letters in it, and also because of the capital N. All right, so if you look at it carefully, you'll see that what we're doing is we're just adding up all the elements in the sample, and then we're dividing by 8 because that's the sample size. And so we end up with a sum of 12 in the numerator. We divide that by 8, which is the sample size, and we end up with a population mean of 1.5. Very, very straightforward. The only difference here, again, is the notation. The calculations are the same as they would have been for a sample, but we do have a population, and that will be important for some of the later questions, especially like, for example, here, you'll notice the variance and the standard deviation are affected by whether this is a population or a sample. So when you read a question like this, the most important detail is right here. Is this a population or is it a sample? That's the most important thing you've got to pay attention to. Anyway, as far as the mean is concerned, as usual, you just simply sort out the elements from low to high. And if you're lucky and there's an odd number of values, then you just find the one in the center. But if not, if you're not so lucky, you just take the 2 in the center. Okay, so here we have 8 observations, which is obviously an even number. We average out the 2 in the middle, and that gives us 1.5. All right, so just by coincidence, they're both the same number. Okay, it doesn't always work out that way. And then the mode, as you recall, the mode is simply the most common element in the sample, or in this case, the population. And because we've sorted the data, it's easy to see that there's 2 1s and there's 2 3s. All right, so those are the only 2 elements that have been repeated. And therefore, that means that our population mode is both 1 and 3. In other words, unlike the mean and the median, where there's a single unique value, here we can have more than one mode. And in fact, you can see right here, I've highlighted them for you. And there's only 2 repeated values. So therefore, we have 2 modes, which are 1 and 3. All right, so, and of course, don't forget too that sometimes there's no mode at all. And when that happens, what you should do is write, there is no mode. And that, you know, we do see that sometimes. In fact, I think in question 1, that's exactly what did happen. That's right. There was no mode in part 1, but here there's 2 of them. And just be aware that there could have been 3 or 4 or 5. There's no limit to how many modes there can be. But in this particular case, it happened to be just 1 and 3. All right, now the range, of course, is simply the difference between the largest and the smallest elements. 4 minus a minus 2, so be aware, of course, that when you subtract a negative number, it's the same as adding it. So our range is 6. All right, now the variance. This is the only really scary formula in this section. And so I've written it down there for you. And you'll notice again, this is clearly a population variance. You can tell because we're using a Greek letter, sigma, to describe it. And then capital N is the size of the population. So, and of course over here we have mu, which is our population mean. Now, let me just split the screen so you can see the data again. So the original data, and by the way, here you do not have to bother sorting them. You do, however, need to know the mean. Oh, all right. Well, you know, whatever works for you, that's fine. You don't need to worry about the formula as long as you understand what you're doing. Because let's face it, the formula itself is really just steps. It's just a very compact way of writing out a series of steps. So if you would rather do steps, that's perfectly fine as long as it works. Okay. So yeah, no, you're not required to do this in any particular way. As long as it works, you're good. All right. Anyway, so now don't forget, we've already determined that the mean is 1.5. So what I have to do is go through every one of these elements one at a time. And you notice I'm going from -2 to 0 to 3 all the way up to the last one. In each case, I'm subtracting the mean, which is 1.5. And then I'm going to square the difference between the two. And when I'm done doing that for each element, I'm going to sum them up. In the denominator, I'm going to divide by the number of elements, which is 8. All right, so now this is the tricky part, filling in these numbers without making any mistakes. So that's why you want to be careful. Whoops. Let's see, I'm trying to fit it all on one page here. There we go. So what I've done here in the second row down here is I've actually calculated the differences first. So you can see what the differences are before you square them. If you try to do this all in one shot, in other words, go to your calculator and try to do this directly, I think you're more likely to make mistakes. This is, to me, the best way to go. If you do it one step at a time, it reduces the risk of mistakes. Anyway, once you're done with that level, the next step is, of course, to evaluate all those squares. Okay, so for this part, I'm going to get rid of the split screen because I want to see it all together. And let's see. Here we go. Let's see if I can fit it all. There we go. So it should be easy to see what exactly has happened. And in the third row, I've actually gone ahead and squared all those numbers and make sure they're all positive, of course. And when you're done, you'll add up the values in the numerator and divide by the population size to get your answer. But as you can see, again, it's really not conceptually that difficult. It's just that it's easy to mess it up. Now, this is also one of the reasons why you want to write out all the steps, because this way, if you make one tiny little mistake along the way, I can still give you partial credit for whatever answer you end up with. That's always nice. I like giving out partial credit, but I have to be able to see what's going on before I do that. All right. Well, let's see what this turned out to be. So it turns out the numerator is 26. There we go. Now I can still see everything. The numerator is 26. The denominator is, of course, 8 because that's the population size. And that ratio is 3.25, and that is your population variance. Now, the last step is easy. Part F is easy. The population standard deviation is easy because it's just the square root of the variance. So that's one of the nice things about variances and standard deviations. Once you've calculated the variance, calculating the standard deviation is very, very easy. All right, so there you go, right there. So the final result, the standard deviation is 1.803. Oops. Okay, that's actually part F. All right, now that one's done. So that was our chapter 12 problem set. Now we can do the sample final, which has all the short fill-in questions, and it contains both chapters 11 and 12. All right, but I think you'll find it to be very straightforward. Okay, so let's get that open. Yeah, I see what happened here. Yeah, I just noticed there's a couple of typos with these letters here. I just want to fix those. That's one of the negative things about this automatic lettering. It messes them up easily. All right, so that's good. All right, so let's get on to the sample final. Let me just make one more little tiny change. There we go. All right, so we're good. All right, so let's move on. And here we go, the sample final. Now here there's a brief review of all the different terms that we learned in chapters 11 and 12, and it's a pretty long list when you come right down to it. So, but our interest right here is filling out the answers, of course. All right, so let's do that right now. So first of all, what two conditions must be met for two events to be independent? So this is coming from chapter 11, our discussion about probability theory. So for two events A and B, or let's put it this way, if A and B are independent, then two things must be true, and this involves conditional probabilities. Okay, so in other words, it must be true the conditional probability of A given B equals the probability of A, and the conditional probability of B given A is the probability of B. And what this indicates is that this shows, and this is not part of the answer, you don't need this part, this is just for your benefit. This shows that the probability of A is not affected by the occurrence of event B, and the probability of B is not affected by the occurrence of A. Okay, so this is all you really need right here. If you wrote that right there, that part, then you'd be all set. Okay, I've kind of expanded it a little bit, but for the test, that's what I'm looking for right here. That's what you need. All right. Now, what is the relationship between an event and a sample space? So formally, an event is a subset of the sample space. Okay. Now, of course, subset means that it is completely contained within the sample space. Like the students in this class are a subset of the entire student body of the school. They're everyone in the class belongs there somehow. So, or you can think of, or how about this one? The odd numbers are a subset of the real numbers, that kind of thing. Now, what must be true for two events to be complements? All right. So, now, and by the way, this one has multiple ways of being expressed. For events A and B, or let's put it this way, events A and B are complements if, all right, so the first thing we can say is that in terms of set theory, we must have A union B is the entire sample space, and A intersect B is the empty set. But if you want to, you can rewrite it in a different way, because it means the same thing to say the probability of A union B equals 1, and the probability of A intersect B is 0. Either one of these is fine, okay, because they both imply the same thing. In some circumstances, though, if you do not have information about the sample space, then realistically, it's the second set that you'll be using. But if you do have all the information you need about the sample space and the two events, then you can use the first definition as well. Okay, but in several cases, you'll have to use the second definition. Either one is fine. All right. This one is easy. If A and B are mutually exclusive, what is the probability that both of them will occur? That would be 0, because it means these are two things that cannot both be true at the same time. Like if I randomly pick a number from the natural numbers and I want to know what's the probability that it's both even and odd, well, then that's clearly not going to happen. So those would be mutually exclusive events. It simply means that they cannot both be true at the same time. So their probability of them both being true would just be 0. Remember, a probability of 0 means something is impossible. All right, now the simplified multiplication rule can only be used when the events are independent. All right, that's the requirement for using the simplified multiplication rule. Not to be confused with the addition rule, the simplified addition rule, when the events have to be mutually exclusive. Here, with the multiplication rule, they have to be independent to use the simplified version. Now here, imagine a scenario where you're picking a card from a deck. Now, based on our understanding of the deck of cards, if A represents the event that the card is red, the complement, which we'll write as A complement, would be the card is black. Okay, now how do you know that? Now, you're not being asked to prove that, but this is true because just in terms of English, every card is either red or black. And more formally, that could be expressed as A union A complement is the entire sample space. And no card is both red and black. Okay, well, obviously not, but formally that would indicate that their intersection is empty. Okay, but just remember, the question doesn't ask you to prove it. They just ask you to come up with the complement. And just remember, you know, the entire deck is, every card is either red or black. All the cards have to be one or the other, but there's no card that belongs to both. Okay, so, and, you know, there's others too that we went over, like, for example, white and black chess pieces, even and odd numbers, that kind of thing. All right, now, how about this one? Oh, here we go. This is a follow-up to what we were talking about before. When is the simplified addition rule used? That's very different than the multiplication rule. Here, the simplified addition rule is used when the events are mutually exclusive. Okay, so they cannot both occur at the same time. Okay, well, what's the relationship between a sample and a population? Well, we could say that a sample is a subset of a population. Now, this is an English definition, so there's a lot of leeway here. You could also say things like, well, you know, a sample is chosen from a population, things like that. But to be very precise, you could say that a sample is a subset of a population, just like an event is a subset of the sample space. Now, this is an interesting one. With a permutation, the order of selection matters. Okay, with a combination, the order of selection does not matter. So if you're stuck on this, you can look at our examples in chapter 11. And you'll see, like, the horse racing example for, let's say, those were permutations, but picking the toppings for Haagen-Dazs, that was combinations because the order does not matter. All right, so that's the difference between the two. Does the order matter or not when we select objects from a larger collection? And then finally, as soon as you see the word arrangements, the minute you see that, you say, factorial. So if I have 5 objects that I want to arrange, there's 120 different ways I can do that. It's just that simple. All right, remember always arrangements and factorial. Factorial tells us how many ways to arrange n objects. All right, nice. Now, oh, look, a problem with samples. Now, you can see right away what's coming. Actually, let me move this down here to make it a little neater. We're going to do some measures on the sample data. All right. So let's get to it. Okay, let's see. All right, so let's take a look at the data. Now, again, right there, don't forget, this is a sample. Make sure you pay close attention to that. Otherwise, you'll have issues with these last 3. All right, the mean, as you know, is simply equal to, first of all, it's X bar because it is a sample. All right, -1 plus 0 plus 5 plus 3 plus 1 plus 4 over 6, because there's 6 elements in the sample. And if you look through it, you'll see that this is 12 over 6, which is 2. All right, nice and easy. Now for the median, I'm going to write this over here. You'll need at some point the sample, the sorted sample. So if you sort the data, you'll end up with -1, 0, 1, 3, 4, 5. All right, that's all we'll need to do the next few. So the mode, you can see that once again, as we had earlier in the chapter 12 problem set, there's no mode. None of these values are repeated. Oh, God, I almost forgot. I didn't do the median. Sorry, hold on a second. I sorted them out and I never got to the median. Let me move that down here. The median would therefore be, here's the 2 in the middle, 1 plus 3 over 2, which is 2. All right, much better. And then for C, yes, you can see for yourselves, there's no mode. Okay, no number is repeated here. Between all of these, there's no repetitions. And then the range is easy because all you're doing is taking the largest minus the smallest, 5 minus a -1, which is 6. All right, now for the variance, we're going to need a lot of room. What I'm going to do is move this data onto a new page so you can see what I'm doing. Or if not a new page, certainly a new section here. Let me just, oh, boy, hold on. And also don't forget, we've already calculated X bar is 2. And also, let's not forget that the formula is right there. And again, you notice since this is a sample, we're using the Roman letter S and we have lowercase n. Oh, whoops, almost. I almost forgot something important. That's n minus 1. Now, the challenge here is plugging in the numbers. And let's see. I hope this fits. All right, let's see what we can do. So we have to go through them all one at a time. And each one of these, we subtract 2. Okay. Yeah, I think I have enough space. And in the denominator, n minus 1 is 6 minus 1. We can write it like that first. All right, and when you're done with that part, you might as well go ahead and just determine what's inside these parentheses. All right, and then the last step would be to actually calculate those numbers before you combine them, of course. So you end up with 28 over 5, which also, of course, is 5.6. And you're done. Wow, all that. So, you know, after a while, it starts to become less and less intimidating. And so there it is, 5.6. Now, what's coming up next, of course, is the standard deviation, which is simply the square root of this. So that's approximately equal to 2.366. So you're literally just taking the square root of 5.6. And then the coefficient of variation, we didn't have that before in the chapter 12 problem set, but we did that in this chapter. And it's also a very simple idea. It's just what you're taking is 2 measures you've already calculated, which are S over X bar times 100. And that's going to be approximately, with a little rounding, 118.3%. All right, well, that one's done. So now we're going to move on and do some probability. And so, this one's going to be a little bit more challenging. So what we're seeing here is a case where we decided to flip a coin 3 times. Oh, now we did in the notes show a way of finding out how to do this with a little table, or sorry, not a table, a graph called a binary tree. The challenge with something like this is making sure that you get the sample space right. Because if you don't, you can't possibly get any of the problems right because you're basing everything on the wrong values. So we're flipping the coin 3 times. Let's take a look at how this would work. So let's jump down here. So it's a pretty simple drawing. Start at the top, and you note that you can get either a head or a tail on the first flip. Once you've had an H or head, you can then follow that up with another head or a tail. If you've started with a tail, you can follow that up with a head or a tail. Now this is easy so far. This is where it gets interesting. If you have 2 heads already, you can get another head, a tail. If you start with HT, you can follow that up with another head or a tail. Yeah, I always run out of room with these things. This one can be followed up with another head or a tail. And then finally, TT is TTH followed by or TTT. So that's the complete list of the sample space elements. So drawing out the graph helps us not overlook any of the possibilities. In other words, this is one thing where people go wrong with this, is that they don't realize that there's 8 possible outcomes when we flip the coin 3 times. Now, in terms of just straight ahead logic, each time the coin is flipped, the number of possible outcomes doubles. Therefore, after one flip, with one flip, we have 2 possible outcomes. 2 flips means we have 4 possible outcomes. And then with 3 flips, there must be 8 possible outcomes. So knowing this will help you avoid the problem of leaving one of them out, which it's easy to do. In fact, you might even miss more than one of them if you're not sure how this works. So the binary tree, I think, is your best bet for not losing one of them. But then, of course, knowing that there's 8 doesn't mean you know which ones they are. You have to have a way of writing them all out. So what I'm going to do for the sample space is write them out in a very specific order. I'll show you why I'm doing this in a minute. Okay, so as I changed the order a little bit, because what I wanted you to see is that first I have all the cases with 3 heads. There's only 1. Then there's 3 cases with 2 heads. And then there are 3 cases with exactly 1 head. And then there's 1 case with no heads. And in fact, interestingly enough, if you remember, we did Pascal's triangle. One, 3, 3, 1 is this pattern you're seeing right here. In other words, the number, well, actually, maybe this isn't the right one. Like, let's just forget that I said that. That's for something slightly different. But this is what you're seeing here is that there's 3 heads, 2, 1, and 0. And by having it organized like this, it's easier to determine which elements belong to different events. Once that's been established, though, it's pretty straightforward. Now, remember, A represents at least 1 head. All right. Now, by writing out the sample space like this, you can see that that means everything except the case with no heads. So I can literally copy this, and there you go. I can't possibly overlook any of them. All right, that's it. Well, at least one head. If you look at it carefully, you'll see the only one I left out was the last one because there's no heads there. And then for B, at least two tails. That would be these cases. Okay, you see what I mean? In each of these cases, there's either two tails or there are three. We're leaving out the cases where there's only one tail or no tails. And also, I just want to point out that in this case, each element in the sample space is equally likely to occur. And that's because heads and tails are equally likely to occur. Okay, so I just want to mention that right up front. Yes, this is one of those cases where the sample elements are equally likely to occur, and that will make our calculations simpler for our probabilities. All right, so remember we did mention that in the slides that there are cases when they're not all equally likely, and then we have to be more careful, but if they are, that makes things a lot simpler. All right, now, of course, you don't have to put all this stuff in here. I mean, all you have to do is follow, answer these questions. But if you don't have the sample space written out properly, then nothing is going to work in this case. So you have to be extra vigilant and careful about the sample space. Now, having said that, the one that you'll actually get on the exam is probably simpler than this one. This would be like a worst case scenario. I think it may only be two heads or two flips, but if it's three, then you know exactly what to do. All right, just in case. It won't be four, let's put it that way. That's for sure. I can guarantee you right now it won't be four. Anyway, with all that finally being said, let's copy these down here so we can see them. Yeah, it's easy to have all the stuff in one place. Now, so the probability of A, because all the elements are equally likely, A is easy because all you have to do is literally count how many elements are in A divided by the size of the sample space. 7 out of 8. I'll make a note here, there are 7 elements in A, and the sample space contains 8 elements. Further, each element in the sample space contains, or is equally likely, is equally likely. Okay, so in other words, you don't have to explain this. Just all you have to do is come up with the 7/8. But I wanted it to be crystal clear here. Why am I writing 7/8? Because there are 7 elements in A, the sample space has 8, and each element in the sample space is equally likely. So I can literally just count. I couldn't do that if they weren't equally likely. I would have to do something different. But I do want to mention here, though, that another approach, which you do not have to do, and you can see why we may not want to do this, because it's such a pain. But this approach would work whether or not the sample elements are equally likely. So it's good to know that this option is available to us. So like I said, no, don't do it this way. Why would you? Unless it's absolutely necessary. Okay. Okay. So you just literally would have to go through. Oh, wait a minute. Something's not right here. I typed this one wrong. There we go. No. No, I did something wrong again. T. There it is. There it is. All right. That's better. Okay, this approach, oh, and again, I'm just putting this in here for your benefit. This approach would be necessary if the sample elements were not all equally likely. Well, here's a heads up. On the test, when you run into this problem, they are all equally likely. So you don't have to worry about this, but it's still, I just want you to be aware of this. You never know when you might need this information in the future. Now, with all that being said, now B therefore must be 4 out of 8 because of the fact that there's 4 elements in B out of 8 total, and they're all equally likely. All right, how about A union B? All right, now again, there's a couple of things we could do, but if you look carefully at this union, if you take these two sets and you look at them very carefully, A has all the elements in the sample space except for the 3 tails, and B does contain the 3 tails. So what that means is that their union is the entire sample space. All right, so just by visually looking at these two sets, you'll see that if you combine them, you're getting all the elements in the entire sample space. So therefore, the probability is 8 out of 8, which is just 1. All right. Now, they don't have to give you the sample space for this to work, but you can see that you end up with 1 because you've got 8 elements in your union. Now, in a similar way, we can look at these two sets and identify their intersection. So why don't I copy these down here again so you can see where they overlap. And well, let's see. Wait a minute. Here we go. HTT, THT, TTH. Yes, right here. I'm highlighting them. You can see the elements they have in common are HTT, THT, TTH. Okay, and so therefore the probability is very simply 3 out of 8. Now, of course, if you really want to, you could use, well, actually, no, we don't want to use the multiplication rule. That's much too complicated. Just count them. All right, now for these, all you have to do, these next two, is use the complement rule, which couldn't be any easier. Just 1 minus the probability of A. How easy is that? And then for this one, let's move this down to the next page. You'd use the same rule. As for, or you can rewrite it as 1/2 if you want to. That's fine. It's just the complement rule. It's so simple. Beautiful. There we can keep them all together. All right, so you can see them all at the same time. Now, this is where they get a little more challenging, okay? So what do I mean by that? These conditional probabilities are done in a very specific way. Okay, this is the formal definition of A given B. So from earlier, we calculated that the probability of A intersect B is 3/8. And B is 4/8. And so this reduces to 3/4. And then similarly, now remember the formula for B given A is a little bit different. The numerator is the same. The denominator is where they're different. So once again, the 8s cancel each other out. And this time we're left with 3/7. All right, now these last three are the conceptual ones. Now don't forget, you're supposed to explain why. In other words, don't just say yes or no. Now, in some of these cases, there's more than one way of explaining it. You can pick any one you want. So for example, here, there's potentially at least 3 reasons to say no. First of all, the probability of A and B, as we saw earlier, is 3/8. Let's go back and double check that. 3/8, which is not equal to 0. All right. Another thing you could say, and you can pick the one you want. A intersect B, as you recall from up here, is, let's see, where is it? There it is. Another way of explaining this is to point out that this is not the empty set. Okay, so that would be another possibility. And a third possibility is to use good old English. Okay. A third possibility is to say, okay, well, A and B have at least one element in common. Any one of those 3 will do the job. You get to pick the one you want. You don't need all 3. All right, now are A and B independent? Now, let's check. Remember, the conditions required. All right, so remember, there's 2 of them. So we're going to start out by checking whether or not the first one is true. So we've already calculated all these probabilities. The probability of A given B, if you recall, is 3/4. The probability of A was 7/8. And so therefore, we know already we don't have to go any further. Since this condition fails, we do not have to check the second condition, we know that A and B are not independent. So as far as your answers go, I mean, really all you have to, this is it right here. Is probability A given B equals the probability of A. As soon as you show that that's false, you're done. You can go stop. That's enough to prove that they're not independent. Okay. So in other words, since but one of them fails, that's it. We're done. All right. Now complements. Remember what it takes to be complements. The two conditions required for A and B to be complements are that they're, in this case, let's use their probabilities. A and B equals 0, and the probability of A union B equals 1. Well, we saw earlier that this one is false. Oh, let me move it down here so you can see. So in our example, the probability of A and B is actually 3/8. So therefore, A and B are not complements. That's it. Even though the second condition is actually true, that's not good enough. All right. So yes, sadly enough, no. I mean, the second one was true, but the first one is false, and that's all that matters. All right. Now we have a joint probability table coming up, and this is Starbucks. Of course, in this hour of the morning, that's all we can think about is Starbucks. So let's calculate some probabilities based on the Starbucks table. And you can see that this table has had all the numbers divided by the grand total. These are all probabilities. So this makes things a little bit quicker. For example, F and D. Now these joint probabilities are easy because you're literally just looking them up in the table. So for example, F and D means French roast decaf. And you just look it up in the table right here, F and D. R&E is regular espresso. If you look over here, that would be 0.10. F comes from the column total for French roasts, 0.46. Oops. D, regular, it comes from the row total for regulars, which is 0.50. D complement is, of course, going to be based on the complement rule. D itself is equal to the row total for decaf, which is 0.50. Now, for these unions, don't forget, all we have to do is use the simplified addition rule. I'll put in parentheses here, note, the columns are mutually exclusive of each other. So we can use the simplified addition rule. Okay, so that's why this is happening. And so when you see that the probability of F is 0.46, and for G it's 0.22, you have a total of 0.68. And let me just quickly split the screen so we can see the table. Whoops. Same thing holds for this one. (0.22 plus 0.32 equals 0.54). All right, then we have two more. These are conditional probabilities, which we'll use the rules for. Okay, so you just write out the formal definition. And then DNF is decaf French roast, which we actually calculated earlier. In fact, we also did French roast before. So that ratio is approximately equal to 0.3913. All right, very simple, very straightforward. And then, let's move this down a little. No, maybe we don't. Okay, hold on. I thought, it's hard to tell how much space. I know what the problem is. Hold on. Yeah, sometimes those page splits are helpful and sometimes they're not. Let me just double check something. I want to make sure I didn't mess anything up. No, everything looks good. Sometimes when you're handwriting in a document, the split screens can really cause problems. Okay. So, oh yeah, we're good. All right. So we have the probability of R and E over the probability of E. Regular espresso, oh, no, what happened there? It has a mind of its own today. Regular espresso is 0.28. E, oh wait, sorry, I was looking at the wrong column, my fault, hold on. It is not 0.28. Regular espresso is way over here, it's 0.10. And espresso, the total for column 0.32. So you got 10 over 0.32, which is, what the hell is going on here? It's decided that it is the boss now. My tablet here has decided that it wants to decide what I'm doing. I don't appreciate that, tablet. So yeah, it's 0.3125. It has something to do with, like I said, this split screen thing really is a pain. I thought it would be very useful and helpful. It's not. It's really annoying me now. All right, that's better. All right, we're all caught up. All right, the technology has been defeated by me. All right, there we go. Thank God. Oh my God. You never know how this stuff is going to react. All right, now let's look at these. Now, these are combinatorics problem. I mean, yeah, combinatorics, which means, of course, the science of counting. It includes arrangements, permutations, and combinations. So if we have license plates that we want to create. 5 letters are chosen from the alphabet where none are repeated. Now, in a case like this, the order of selection does matter. We are selecting 5 letters from 26 where the order matters. For example, license plate A, B, C, D, E is different from license plate E, D, C, B, A. Okay, so therefore, each choice of letters for the license plates is a combination. So therefore, we have N equals 26, R is 5. So how does that work? Oh, one more thing. Let me remind you what the formula looks like. Okay, so now basically we just plug away And don't forget, this operator does appear on your calculator. So here we would have 26 factorial over 5 factorial times 26 minus 5 factorial. So this can be simplified a little bit. Now, this is a very messy process, but, oh, what did I do? I'm sorry. I just completely realized I screwed up royally here. These are permutations. Oh, it's just too early. I apologize to everyone. I just realized I completely lapsed this up. These are permutations. This is completely my fault. I don't know what I was thinking. These are definitely permutations. All right, let's do this again. Sorry about that. Oh, man. It's been a long semester. Wait, no, that's fine. This is what I wanted to change. All right. Okay, so it's n factorial over just plain r factorial. That's so much better. N minus r. Okay, n minus r. There we go. All right, so then in a case like this, we're going to have 26 factorial over 21 factorial. So on your calculator, let's get that straight. How would you approach this? So the sequence of strokes that you would need is pretty straightforward. Let me go get my calculator out real fast and remind you how this is done. Now, if you have one of the more advanced calculators, the instructions will be a little bit different. So you're going to just type 26 factorial. Uh, 26 factorial divided by 21 factorial and then don't forget the equal sign. Oh, now mine, hold on, it looks like I made a typo. 26 factorial divided by 21 factorial equals, yeah, that's it. And it's approximately, now, if you notice, they ended up giving you something with a bunch of zeros after the decimal. It has to be an integer. It's 7893,600. So if the calculator gives you a tiny fractional part at the end, ignore it. It has to be an integer. I didn't notice this until now. I'm not quite sure why this is happening. It has something to do with the way they're calculating factorial, but you can ignore any fractional part if you get one. It's just 7,893,600. All right, so that's a lot. Now imagine if we needed to have 10 letters in our license plate. I mean, you know, it gets pretty big. Let's just put it that way. So now, of course, you can see why this is important. Why would a state like New York or Connecticut have 3 numbers and 3 letters? Because there's a lot of cars in those 2 states. And so 7 million choices would not be nearly enough. So that's why they have so many letters and numbers. All right, now that's done. Now this one, there's a bakery and they have a new style layer cake, which the customers can choose any 3 flavors from 6. All right, so this time, unlike what I said before, here the order of selection does not matter. So each choice is a combination. So we have N is 6 and R is 3 because we are choosing 3 flavors out of 6. And the factorial, the combinations formula is so we'll plug these in. Now this number won't be that large. So let's do this. Let's simplify it a little. Now for this one, 6 factorial is simply 720. 3 factorial 6. For something like this, you might as well just write it in because they're relatively small numbers. And you should end up with 20. All right, so you can have 20 different choices for your cake. All right. Now, finally, there's in part C, a homeowner has a bookshelf with 3 titles. Now, we've done examples exactly like this. One of the titles is Why Everyone Loves Math. That might be a big bestseller. You should look at the New York Times and see if it's there. Why Everybody Loves Math. If nobody's written that book, I think I will. How does that sound? I'll spend 2 years writing this book and I'll sell about 6 copies. Why Everyone Loves Math. The Mathematics of Opera and Mathematicians Are Cooler Than You. That one people might actually buy because it sounds like a challenge. Anyway, but how many different ways can these titles be arranged on the bookshelf? So these are arrangements, all right? So each way in which the titles can be arranged, well, is called an arrangement. There are n factorial ways of arranging n objects. Okay, since there are 3 books, the number of possible arrangements must be, so I'll write this down here, 3 factorial, which is 3 times 2 times 1, which is 6, and that's it. You can arrange your books 6 different ways. As we saw with the parking garages, we had 3 cars, and we figured out that there are 6 ways of parking the cars. If you wanted to write out all the arrangements, you could certainly do so, but there's no need because we understand how this works. But if you like to double check your results, you can certainly sit down and write them out, and you'll see that it will in fact be 6. All right, well, that was pretty intense, but because we're done, we've earned ourselves a day off. Monday was supposed to be our last day. We are completely done with the course. So therefore, you get a day off on Monday. Woohoo! And you should probably use that time to work on your take-home final exam. It'll be the same format. Everything's the same. Just download it, do it, take pictures, send it back, and we'll be all set. All right. And so you can have until next Thursday. I think that'll be more than enough time. And also, by finishing early, you get a head start in your other classes. You can start now before your other finals get started, or whatever else you're doing for your tests. I know that if you're in performing arts, of course, you don't have tests. You may have to do a play or do a dance or whatever the case may be. But here you can get this out of the way early if you want to, because we're finished so soon. So, all right. So I hope that at this point you're sitting there and thinking, wow, my math knowledge is so much better than it was 3 months ago. And I will remember these skills that I've learned for the rest of my life. That would be nice. And even if not, you'll certainly be a lot more familiar with all these ideas. And whenever you need some of this information, you'll have it right at your fingertips. So that's all we can really ask for. so that mathematically you're in a much better place than you were 3 months ago. And you never know where that can take you. So I hope that everything goes great for the rest of your semester. And well, you never know when it might bump into you again. You might suddenly find yourself thinking, you know, I can't live without math. Maybe I'll do something more advanced. You never know. It could happen. So we've got plenty of math courses for you to take if that happens to be the case. All right. So now, if you do run into trouble, you can send me emails while you're working on this thing. But other than that, we're done. So if there's no last minute questions, I'll just say goodbye to you all.
Thank you so much.
All right. You're welcome.
Have a nice summer.
All right. You too.
Thank you.
All right. Bye.
Thank you so much.
All right. Bye. Oh, I hope you liked it. I really do. All right.